In this section, we discuss the example of a particle confined to a box. This is the simplest example of the new and somewhat strange physics of quantum mechanics, and an example that we will come back to from time to time. Imagine we have a particle, such as an electron, confined to a box where the edges of the box are at x equals 0 and x equals a. By confined, we mean that the electron can have any position between x equals 0 and x equals a, whereas outside the box, it has zero probability of being found. We set up this problem by defining the potential energy of the electron as a function of position, or v of x, shown by this green line. For example, in classical physics, v of x could describe the gravitational potential energy, where the green line describes the height of the road or track that our red particle rolls on. If our particle rolls down to a region with lower potential energy, it will have a higher velocity or higher kinetic energy due to the conservation of energy. To ensure that our particle is confined, we can say for now that the potential outside the box is infinity, whereas we will say that potential inside the box, for convenience, is zero. In this way, the kinetic energy of the electron is also equal to its total energy, and that energy is never enough for the particle to climb outside the box. In order to find the behavior of an elementary particle using quantum mechanics, we need to solve the Schrödinger equation. The Schrödinger equation is a differential equation where the Hamiltonian contains the kinetic energy term plus the potential energy term, and that is equal to the total energy term using the energy operator. Since we are solving a one-dimensional problem with only x as a spatial variable, we can replace the Laplacian with the second derivative with respect to x. To simplify this problem further, we will use separation of variables to get the time-independent Schrödinger equation. To do this, we separate capital psi, the total wave function, into lowercase psi, the time-independent wave function, times a function dependent only on time. When we start substituting capital psi into our differential equation, we first notice that the w function can be pulled out because it has no spatial dependency. Then we bring down the minus h bar squared over 2m, leaving us only with the second derivative of now the time-independent psi with respect to x. For the potential term, we can simply bring down w_v psi. Similarly, for the other side of the equation, the time derivative only affects the w function and not psi. Therefore, we have lowercase psi, I h bar, the time derivative of w. If we now divide both sides by our full wave function capital psi, we will finish the separation of variables. Dividing the kinetic energy term here divided by full psi removes the w term and brings down a psi down here, giving us the equation shown on the left here. Similarly, the potential term divided by full psi gives us just the potential v. And finally, on the right, dividing by full psi removes the time-independent psi and brings a w on the right. This equation has the x and t variables fully separated because all of the x-dependent functions, the lowercase psi, are over here, and on the right we have only the time-dependent functions w. This means we can solve each side independently. So for example, we can solve the time-dependent side on the right simply as I h bar, the derivative of w with respect to time divided by w equals our energy. Since E is simply a number, this is a simple one-dimensional differential equation that we can solve using calculus. We recognize that the solution to this differential equation is simply an exponential, where in the exponent we have energy divided by I h bar, or e to the minus I energy over h bar times time. And we have a constant of integration we will call A1. When we plug this solution back into our differential equation here, we get an equation that's simply a restatement of the time-independent Schrödinger equation, or the Hamiltonian operator operating on the time-independent part of psi equals E, which is now simply a number, times the time-independent wave function lowercase psi. In summary, separation of variables in one dimension allows us to change the full wave function capital psi into a lowercase psi, which doesn't depend on time at all, and time only comes in through this factor, which simply changes the phase of the wave function. Inside our box, V equals 0, which means we need the solution for a free electron. After separation of variables, we are left with having to find only the time-independent wave function and using the time-independent Schrödinger equation. By free electron, we mean that the potential V equals 0, which simplifies our Schrödinger equation by removing the potential term V entirely. The solutions to this differential equation are waves of the form e to the I kx or e to the minus I kx. In fact, this differential equation is often called the wave equation. Remember that psi can have real or imaginary parts, and so the constants of integration, such as a and b, can also have real and imaginary parts to them. Remember that for a second-order differential equation, we have two arbitrary constants, here a and b. Because these constants are arbitrary, we could have also written the solution to this differential equation as a1 cosine kx plus b1 sine kx, where a1 and b1 are also arbitrary imaginary number constants. Now, by plugging our solution into our differential equation, we will give the requirement for k. Here we need to do the second derivative with respect to x of our wave function, which brings down I times k squared, or minus k squared. This minus k squared then multiplies with the minus h bar squared over 2m to give us a value equal to energy E. Thus, the energy E determines the wave number or wavelength of our wave, in addition to also the frequency of our wave. Notice also that since k squared is proportional to energy, k can be either positive or negative, but it must be real. The wave function that we found in the previous slide for the free electron is also the solution to the Schrödinger equation for the particle in a box for the region of V equals 0 inside the box. The requirements of this solution are that the wave vector k must be related to energy such that E equals h bar squared k squared over 2m. The prefactors a and b of the free electron solution were not specified, but for the particle in a box, we will determine them using the boundary conditions. In our infinite potential well problem, the walls of our box rise infinitely high. This means that the probability of finding our particle outside this box should be 0. Thus, the wave function outside the box should be 0 and continuous up to the point of x equals 0. This establishes a boundary condition at x equals 0 such that psi of 0 should be 0 when x equals 0. That happens naturally if the wave is of the form sine kx, because sine of 0 is 0. However, because cosine of 0 is 1, any form of the solution that is of the form cosine kx must have 0 as the prefactor to eliminate it. Thus, we are left with the form of the wave function of a sine kx. Similarly, at x equals a, the wave function must also be 0. Thus, sine k times a should equal 0 is another boundary condition. Recall that sine of an angle equals 0 when the angle is an integral multiple of pi, such that ka then must be n times pi, where n is an integer. Solving for k then, the boundary conditions require that k be an integral multiple of pi over a. We call n the quantum number because this condition comes from quantum mechanics, and we say that k is quantized because it can only have specific values depending on the quantum number n. Now, because energy depends on k, energy is also quantized. Substituting k equals pi over a times n gives the quantization of energy that energy equals h squared over 8m times the quantum number n squared divided by a squared, where a is the length of the box. Now, because our wave function psi is non-zero only within the box, we can easily normalize it to find the prefactor a. To do this, we use the condition that the probability of finding the particle from the wave function anywhere in the box should be 1, or that the integral of psi star psi should equal 1 when I integrate the wave function between 0 and a. To do this, I will need to know the integral of sine squared kx. Then, using the formula for sine squared kx, one can then solve for the prefactor a in terms of the length of the box. In this figure, we show what the wave function psi look like. Let's start with n equal to 1, the lowest energy wave functions. In this case, psi of x equals sine pi x over a. That corresponds to this wave function psi sub 1, which starts at 0, rises, and then comes back to 0 at x equals a. In that case, sine when x equals a is sine of pi, which equals 0. For n equals 2, the wave function psi sub 2 goes through a full wave cycle before again reaching 0. This wave function when n equals 2 has 4 times the energy of the n equals 1 state, which we call the ground state because it has the lowest energy. Psi sub 3 has 3 half cycles, while psi sub 4 has 4. All of these are higher in energy. Notice that the ground state wave function is the smallest wave that will fit within our box, whereas higher energy waves fit successively more waves within the same space. One can also see that the higher energy waves are more wiggly than the low energy waves. Remember that in classical mechanics, an electron can have any energy while it's inside this box. But in quantum mechanics, only specific energies are allowed for the particle's wave functions. Those energies are given by the quantization condition E equals h squared over 8m, n squared over a squared, where the quantum number n is used to specify the energy of each level. The quantization of energy is a strange new feature of quantum mechanics not found in classical mechanics. The quantization of energy, momentum, and other properties is found universally throughout quantum mechanics. We will often come back to this example of particle in a box whenever we wish to understand quantization. Another common feature of quantum mechanics is that the ground state energy, here shown as E1, is not zero. That's because it takes a finite wavelength wave to fit within our box, and this smallest wave has energy greater than 0. Another feature that we will see throughout quantum mechanics is that the ground state wave function only goes to 0 where it is required by the boundary conditions. The first excited state, or wave function with next higher energy, goes to 0 at one point in the middle of the box. The second highest wave function goes to 0 at 2 points within the box, and successively higher energy wave functions will also have more zero crossings that we call nodes. Recall that the probability of finding the particle at a particular x within the box is proportional to the square of its wave function. The probability densities then of a particular wave function goes to 0 at the node where the wave function crosses 0, while the electron is most likely to be found near the middle of the box when it's in its ground state. When the electron is in its first excited state, it actually has 0 probability of being found in the exact center of the box. In general, as we look at wave functions with increasingly higher energy, we see more nodes and more curvature. Another feature that we will see throughout quantum mechanics is that the wave functions have some symmetry about them. The ground state wave function, for example, has a center of symmetry in the middle of the box. The first excited state wave function also has a center of symmetry, although it is positive on one side and negative on the other side. We call this type of symmetry antisymmetry. As we look higher in energy, the wave functions alternate from symmetric to antisymmetric. The symmetry of these wave functions is often called parity, where the wave functions have either even or odd parity. The probability densities, on the other hand, are always symmetric. The probability of these wave functions is always positive because the wave function is multiplied by itself. One can imagine, however, that if one wave function is multiplied by another wave function, we would get as much positive as negative influence, such that the sum of the product of two wave functions would be 0. We will use this feature of the wave functions later, saying that these wave functions are orthogonal. It can also be shown that any wave function for an electron inside this box can be made up of a sum of these wave functions with discrete energy levels. Thus, our set of wave functions described by quantized energy levels makes a complete set that can describe any wave function.